but we haven't discussed last time, or I just started to discuss last time, how to actually find complicated limits. Now, for this task, we use the so-called limit laws. Now, maybe today let's start with another example, just to warm up. For instance, let's choose the example x squared if x is rational and 0 if x is irrational. Okay, so for this function, if you consider the limit f of x as x approaches 0, what will happen? 0. Who can prove it? By proving, I mean I give you an epsilon. What is the delta? Right, yeah. Square root of epsilon. So actually here, in this example, you see this easily from the graph. Of course, the graph of such a function is complicated to plot. But we can, it will be something like this here. Okay, now, what we have given is the epsilon. So we claim that the limit is 0. What we have given is the epsilon strip. Okay, and the one possible delta you can choose, you see here. You just look at this domain here. So this is one possible. This is one possible delta, and that's the one which you found, square root of epsilon. So actually, this is best possible from this point of view. So you see already here that if you choose the delta to be the square root of epsilon, then for all those x here, the function value of this function lies within the epsilon strip. And using this argument, we have proved that this limit relation holds here by the epsilon delta definition. Okay. Today we will see there is actually a much easier method to do this, where we do not have to use the epsilon delta definition anymore. Now, if you replace 0 by anything else, what is the limit? Right, it doesn't exist. Actually, this is the same situation as one of the examples you had to prepare for this homework. Okay, namely the example where you are 1 at the rationals and 0 at the irrationals, or the other way around. The reason is, if you just fix, just roughly, the reason is, if you, for instance, if this here is a rational number, okay, so the function value is this here. Now, obviously, you can find, if you choose an epsilon strip like this here, okay, no matter how close you get to this point here, in this interval, you will always have irrational numbers. But irrational numbers are mapped to 0 outside the epsilon strip. Okay, so roughly, this is the argument. And you can do this. So this value cannot be the limit. Okay, you can use the same argument for all other values. Okay, because as I have explained last time, proving that the limit does not exist is actually more complicated, because you have to prove that the limit is not equal to any L. Okay. Of course, the first choice is the function value itself. Okay, but also for all others, you can use the same argument. Now, of course, this is not precise, but you can easily write this down, this argument, precisely. Okay, so any questions here? Now, today we will essentially see that this example is getting much easier by using the limit laws. In particular, we will not have to go back to the epsilon delta definition of the limit. We can directly prove it. Now, last time I told you already that we will obtain limit relations by using limit laws. Now, last time I already wrote a couple of limit laws on the blackboard, so the assumption is always that we have given two limit relations. Then you have a couple of laws, like if you consider the limit of a sum as x approaches a, then what you get is the sum of the limits. The same is true for the difference. Then the same is true for a product The same is true for the quotient. Then another limit law is if you have a constant times a function and then the limit as x approaches a, this is equal to the constant times the limit. And you have some basic rules, like some limit relation for some easy functions, like if you consider the limit of a constant, what you get is the constant. And if you consider a limit of x, then what you get is a itself. So we use normally the epsilon delta definition to prove such relations, and using such simple laws, we can now find out much more complicated limits. That's the basic strategy. We saw last time already how to prove the first law. Okay, the others are proved similarly, but more complicated. For instance, it's a little bit more complicated. You can, as an exercise, you can try to use the epsilon delta definition to prove something like this on your own. Now, maybe I should emphasize something. What is important here are the assumptions. This is something which is easily overlooked. Now, the assumptions here are that those two limits exist. Okay? So you should, for instance, the first one you should read in the following way. If this limit exists and this limit exists, then this limit here exists as well and is equal to the sum of the limits. That's the way you should read this theorem. Okay? Now, if those limit does not exist, one of them or both, this is not necessarily true. Okay? It's not necessarily true, for instance, that a limit of f of x does not exist, a limit of g of x does not exist, that then the limit of a sum also not exist. Okay? It's not necessarily true. Okay? So those limit laws you are just allowed to apply whenever the assumptions are satisfied, namely those limits here exist. Okay? For instance, an easy example, situation where those two limits do not exist, but the sum here exists, okay, would be you choose here the a is equal to 0. You choose the limit of 1 over x squared as x tends to 0, does not exist, is infinity. And here you choose the limit of minus 1 over x squared as x tends to 0. This limit does not exist as well. Okay? But the sum exists, because if you sum those two functions, you get 0. Okay? And the limit because of this law here, 0. So this remark seems to be trivial, but I know from experience that students often overlook this. Okay, so those limit laws just hold if the two limits here exist. Okay, I will say a little bit. I will show you some examples later on where you get something wrong if you apply those limit laws for limits which do not exist. Or you might get the right answer, but the way you argue is wrong. Okay, so actually from those limit laws, as a consequence, you get already some consequences. For instance, a very easy consequence is that if you look at the nth power of a function as x, if you look at x to the n, actually also this is true. If you look at the nth power of a function, now if you use the product rule again and again, you get eventually that this is equal to the limit of f of x as x tends to a to the n. Okay, so this is already a consequence, okay, from the product rule. For n is equal to 2, okay, you apply it twice. And if you have three functions, you apply it once. And if you have three functions, you apply the product rule twice, and you get this rule here. By induction, you get the general rule. Now, this has, for instance, the consequence that the limit of x to the n as n tends to a is equal to a to the n. Okay? And if you combine, so for a power function, it's very easy to find the limit. You just evaluate at a. Okay? And if you combine this with the sum rule, and then with the multiple constant rule and so on, you easily get that whenever p of x is a polynomial, then you get that the limit of p of x is p of a. So very simple in this situation, you just plug in. This is already a consequence from the basic limit laws. Okay. Then if you look at the rational function, a rational function is a quotient of two polynomials, and a with q of a is not equal to 0, then we have that the limit of f of x as x tends to a is equal to f of a. Okay, so also for rational functions, so such functions are called rational functions. Rational functions are just quotients, polynomials. Okay, also for rational functions, you get that the limit is very easy to compute, just plugging in. And this here is, again, a consequence from the limit laws. Once you know this here, and you know that the quotient rule is true, so that the limit of a quotient is the quotient of the limits, you immediately have this here. Okay, so for polynomial and rational functions, the situation is very easy. Now, this kind of terminology, polynomial, rational functions, please memorize it. If you encounter such situations, for instance, such notation in the in-class homework, and you do not know what it is, you can look in your textbook. There is an index at the end, okay? And the index normally will contain all those terminology. But this terminology you should memorize. Okay, so the situation for rational functions is very easy if the rational function is defined at a. Okay, but if the function is not defined at a, of course you can still consider the limit, and also in those situations you can use the limit laws. This is something you have already done in high school. For instance, if you are interested in the limit x tends to 2 of x minus 2 over x squared minus 4, okay, then in this case you have a rational function but if you plug in 2, the rational function is not defined. So here you have to do it different. Okay? But we know that that this function here is equal to 1 over x plus 2. Okay? If x is not equal to 2, those two functions are equal. Those two functions are not always equal. Okay? Because for x is equal to 2, this function is not defined. But this function is defined. Okay? So those two functions, strictly speaking, are not equal. But because of in the limit definition, x has to be away from 2, okay, we can replace this function here by this function. And now this function we can easily evaluate. Now we apply the quotient rule, so we can take the limit in the numerator and denominator. And here we have just a polynomial, so we plug in. Okay, so also this here follows now from the limit laws. Now, another limit law is the following one. So the limit as x tends to infinity of x is equal to the nth root. Nth root of a. Okay. Of course, if n is even, a must be larger than 0. Now, this is one of the limit laws. So this means we have to prove it by using the epsilon delta definition of the limit. So for this function, you can try it on your own. It's not so easy to prove it by using the epsilon delta definition, but it's possible. I think in our textbook, there is an exercise for the case n is equal to 2, and you have to use the epsilon delta definition to handle this case. You can try it. It's not so easy, but this is something we have to prove by the epsilon delta definition, because this is for us a limit law. And we will see later on that from this limit law, we will get that the limit of the nth root of any questions? We will see from this limit law that this will imply that the limit of the nth root of a function f of x as x tends to a is equal to the nth root of the limit of f of x as x tends to a. Now, again, you need that n. If n is even, this should mean if n is even. So if n is even, then this limit must be larger than 0. Okay, so we first have to prove this by using the epsilon delta definition. Later on, we will see this will follow from this. Okay, now we can accept those two also as limit laws, and using those two laws, we can even compute more complicated limits. Namely, we discussed last time the following limit. Okay, so now you know already the main trick from high school. So what we do is we multiply the numerator with square root of t squared plus 9 plus 3, and do the same for the denominator. Okay, now you get that this is the limit as t tends to 0. So the numerator becomes t squared, and we can erase this with this t squared here. So we get 1 over t squared plus 9 plus 3. Okay, maybe once more, I stress once more at this point that those two functions are not the same. Okay, because this function here is not defined that t is equal to 0, but this function is defined, so they are not the same. But we can replace this function here by this one, because this symbol here, okay, tells us to stay away from 0. So it doesn't matter that this function at 0 are different. And here we can now again use our limit laws. We can first put the limit in the numerator and denominator. For the numerator, we have already proved that the limit is 1. For the denominator, we can use the sum rule. So we can write the limit of this sum as the sum of the limits. For this, no problem. And for this, we have just seen that we can take the limit under the root. And this is a polynomial, so we can plug in. Okay, so this is the general strategy. So you see how to build from the limit laws more complicated limits. So this will give you eventually, if I do this, I'm not writing out every step, but if I do this, you will get 1/6 as the limit. Okay, I know you have learned this in high school, but you should see here the difference. Okay, we start from the epsilon delta definition. We prove some basic limit laws. The limit laws you can see is some tools. Okay, and we prove for some basic functions what is the limit, and then we use our tools to build more complicated functions. And in doing so, we can avoid always going back to the epsilon delta definition of the limit. Okay, now we have already seen that a very convenient tool for proving that limits do not exist are right and left-hand limits. And I showed you already that there is a theorem which tells you that the limit of a function exists if and only if the right-hand limit exists and the left-hand limit exists, and they are both equal. Okay. Now, also something like this here. To prove this, you have to use the epsilon delta definition. Once you have proved this, you can accept this as one of the rules, and you can apply it. Okay, and then you do not have to definition anymore. I should mention that the limit laws also hold all of them. Okay, for right-hand limits and left-hand limits. Now, also this here is convenient. We have seen already before. So, for instance, if you have the function x over the absolute value of x, you see that, okay, and you are interested in the limit of f of x as x tends to 0, then you'll first look at the left-hand limit. Now for the left-hand limit, we can replace our function, because x is now negative, we can replace our function by -1, but for this one, we know already that the limit is -1. This is one limit law. Now for the right and left-hand limits, and you do the same. With the right-hand limit, so here you have 1, so you get 1, and you see that those two here are different. So the limit does not exist, as we know, of course. Okay, so this is quite easy, but you should see that I used here this result here. So here I do not have to use the epsilon delta definition anymore, because the epsilon delta definition was already used by improving this result here. Now, maybe a slightly more interesting example is this one. Okay, so if you, without thinking, if you just apply the product rule, you would see that, okay, this is the limit of this product is the limit of this function times the limit of this function. And the limit of this function is 0. Okay? So you would get 0. This answer is correct, but to deduce it like this is wrong. Okay? because you can just apply limit laws if the limit of both functions exist. And we know already that the limit of x over absolute value of x does not exist. So here you are not allowed to use the limit laws. Okay. Also, you get the right answer. Now, again, you have to look at left-hand limit. So here you get minus sine of x, and you can just plug in, so you get 0. And for x tends to 0 from the right, you get sine of x, and you just plug in and you get 0. Actually, we haven't proved this relation here, strictly speaking, because they are not part of the limit laws. Okay, so for those functions, you can either see it. The problem here for those functions is that we haven't defined them precisely. So using here the epsilon delta definition to prove such limit relations, okay, wouldn't make a lot of sense. But you see already from the definition, from the graph, okay, that this is satisfied here. But once more, the essential thing here is you are not allowed to write that this is equal to the limit x tends to 0 of x over the absolute value of x times the limit of sine of x tends to 0. Okay? Even so, you would get the right answer here. This is not true, because the limit laws just hold if the involved limits all exist. Okay, so any questions on this? I see this quite often, that students are doing it like this. Okay, be careful here. Now, there are a couple of more very convenient laws. I just write them as theorem. The first one is if you have two functions and you know that f of x is smaller or equal than g of x for x close to a, and you know that the limits both exist, then you can conclude that L is smaller or equal than R. Okay, so this is obvious guess from the definition of the limit. So if you have such a relation for all x close to A, and the limits do exist, this relation will also hold for the limits. Okay, so I guess everyone will accept this as a true theorem. Now, maybe just for this theorem, because this is maybe a little bit more tricky to prove. So maybe for this theorem, I just want to show you the proof. Now, maybe some of you are not so interested in mathematics, so for those, the proof is not so important. Okay, but the interesting thing about this theorem is that the proof involves a general idea. Now, this general idea you might have learned already in high school, which is called proof by contradiction. If you want to prove something like this here, a general method is you assume it's wrong, and then you try to find a contradiction. Okay, you know this word? You all know this word? Contradiction. You know it? Who doesn't know it? Maodun. Okay, so this method which I use is called proof by contradiction. Okay, 反证法. Okay, so we assume that this is wrong. Okay, so L is larger than R. Okay. Now, you see already, we know that those two limits exist, okay? And we have already proved that if two limits exist here, then the limit of the difference also exists, and this is the difference. Okay, so we know that the limit of g of x minus f of x as x tends to a, okay, also exists because those two limits exist, and is equal to r minus L. Okay. Now, what does this mean? This means whenever I give you an epsilon, you can tell me a delta, such that if x is close to a within a delta distance to a, the g of x minus f of x will be close to r minus L. Okay, so the g of x minus f of x minus r minus L will be smaller than epsilon whenever x is sufficiently close to a. Okay. Now we choose a special epsilon. Namely, you choose for epsilon L minus R. Okay. Now, observe that this here is larger than 0 by assumption. Okay, because we assume that this holds here, so that our theorem is wrong. So this is larger than 0. So you can use this epsilon. You will get a delta such that this holds here for this epsilon. Okay, so you will get that the absolute value of g of x minus f of x minus r minus L will be smaller than L minus R whenever x minus a is larger than 0, smaller than some delta belonging to this epsilon here. Okay. Now, if you look at this here, this will imply, observe that that x is smaller or equal than the absolute value of x. This is always true. So you can actually forget about the absolute value, and then you see that you can erase this here. So from this you get that g of x is smaller than f of x. Okay. Whenever x minus a is larger than 0 and smaller or equal than delta. But this here is a contradiction, because we have assumed that f of x is smaller or equal than g of x when x is close to a. Okay, so we are finished. So this was wrong here. So L is smaller or equal than R. You see, for this example, it's not so easy to prove it. You need an idea. Namely, here the idea you need to have is to find the right epsilon. Okay, to prove this. It's a little bit tricky. Not very complicated. So the proof is finished here. I told you I am doing this here. The proof is finished. Okay, because we have a contradiction. You find this in our textbook. In our textbook, at the end there are some appendices, and there you will find such proofs. You will not find it directly in our textbook, so not at the section, but you will find it at the end. Now, this is just for students who are more interested in mathematics. I mean, that you understand how to prove such things is not so important. This is not part of your training here. Your training is more directed to solving examples, okay, but also understanding basic concepts, but not really proving. This is something we would emphasize if the students are students of our department, the Department of Mathematics. Maybe this method is called proof by contradiction in English. Now, there is one more limit law which is very, very useful. This is sometimes called squeezing theorem. Or sandwich theorem, or pinching theorem. It has a couple of other names. So this theorem tells you, and this theorem we will use many, many times throughout this lecture. So this is a very important tool. If you have now three functions, and you have such a relation for those three functions, if x is again close a, and you know that the limit of f of x as x tends to a exists, and also the limit of h of x as x tends to a exists, and they are both the same, okay, then you can prove. You see that this function is sandwiched between the two other functions, okay, and you can consider this is the bread, okay, and this is some ham, okay. Now, if you see that this relation holds, and in particular, if x goes to a, okay, this function will approach L, and this function will approach the same L, okay. Now, because this function is sandwiched between those two, okay, this function doesn't have any chance, okay, but to go to tend to L as well. So from this you get that the limit of g of x as x tends to a also exists and is equal to L. Okay. So actually you should, again, this theorem tells you if you have this relation, if those two limits here exist and are equal to L, this limit exists as well and is also equal to L. So actually you should read this as two parts. The first part is that this limit exists, and the second is it's equal to L. Okay, it tells you existence and at the same time what is the value. Now, this result is very useful. In particular, so maybe let's first look at the easy example. Okay, so this is the function we have seen today in the in-class homework. The integer which is small, the largest integer smaller equal than x. Maybe in high school you have used another notation. The reason why I use this notation, because maybe sometimes we will also talk about this function here. Okay. So this is kind of the opposite. So here you have the smallest integer which is larger equal than x. This is the largest integer which is smaller equal than x. So this function of, if x is 2.5, this function will be 2 and this function will be 3. Okay. Now, maybe you know why this notation. This notation, in English, this is called the floor. And this function is called the ceiling. Okay. Because 2.5 is in the middle, the floor is 2 and the ceiling is 3. Okay. So this is our notation we are going to use. Now, for this function, if you plot the graph, it's very... So the graph of the floor, okay, okay, you have something like this here. Then the function is jumps. Then the function jumps again. And you have here. Okay, so this here should be 1, this should be 2, this should be -1, and so on. Now, if we are interested, for instance, in the limit of f of x as x tends to 0, okay. Now, of course, you could use left and right hand limit, okay, and it's easy to figure out. But you see that for x close to 0, okay, which is the important thing, this function here, f of x, will be sandwiched between. So this function is larger or equal than -1. So you have -x squared. and smaller equal than 0. Okay? So this relation will hold if x is close to 0. And now you see that this limit here is equal to 0. This limit is equal to 0 as well. So the limit here has to exist and has to be equal to 0 because of the sandwich theorem. Okay, so you see, as x tends to 0, this here will tend to 0. This, of course, will tend to 0. But again, f of x is sandwiched between those two. So f of x will tend to 0 as well. Okay. So you see already here is quite helpful. You do not have to use left and right-hand limit. You immediately use this result, and that's it. So this is very helpful. Any questions to this example? Now, actually, the result can also be applied on this function. Okay. We proved that the limit of f of x as x tends to 0 is equal to 0 by using the epsilon delta definition. Another way would be, you see that the f of x obviously is larger or equal than 0 and smaller or equal than x squared. Okay. Now you see that, okay, this is our f of x, this is our h of x. You see that this tends to 0 as x tends to 0, tends to 0 as well. So f of x, the limit must exist and equal to 0. You do not have to use any more epsilon delta definition. Okay. Even so, the function is more complicated. This is maybe the most easiest way to see it. And from here, you should also understand what the use of the limit laws is. Namely, we can avoid now having so much information. We can avoid now always going back to the epsilon delta definition of the limit. We just use what we already know in order to build more and more complicated, deduce more and more complicated limits. Okay. I haven't proved this. You are invited to do it on your own. It's not so complicated to prove it. Or you just look in our textbook. Okay, so any questions to this? And actually, this is the way you should also argue, okay, from now on, because we have now the epsilon delta definition of the limits, and we have those precise tools, okay. Now, in order to figure out limit relations, you should use those tools, okay, in order to prove limit relations. Or if you cannot use one of the limit laws, you have to use the epsilon delta definition. Because everything else is not precise. Okay, now I will jump on to section 2.6, which is about limits at infinity. Now, actually, this is something which is quite similar to what we have discussed already so far. The only difference is, so this is another kind of limit notation. Okay, our notation of limits do not cover, so far do not cover one situation, namely, which is interesting as well. Namely, if you look at the function x squared minus 1 over x squared plus 1, and you plot the graph, you will see that at 0 you have minus 1, so you will see that the graph, and this is symmetric. So if you plot the graph, it will look roughly like this here. Now, you see that if x is getting larger and larger, this function seems to tend to a limit as well, namely 1. And this is one more notation of limits we haven't covered yet. So you see that we are intended to write that the limit as x tends to infinity of f of x is equal to 1. Okay. The difference to our previous situations is that previously here we had a fixed given number. Now we have infinity here. Okay. But the meaning of this symbol should be clear, namely as x is getting larger and larger, f of x is getting closer and closer to 1. And you see, actually the same is true for the limit of f of x as x tends to minus infinity. So you get here 1 as well. Okay. Now, of course, this is not a definition. We can also give a precise definition. Okay, so such a relation what does it mean? So again, of course, we give a epsilon larger than 0 because we want to make the distance between f of x and 1 as small as possible. Okay, smaller equal than epsilon. Now, for such an epsilon, there must exist some m, okay, which might be a function on epsilon. Okay, large enough such that the distance between f of x and 1 is smaller equal than epsilon. X is large enough, larger than this m here. Okay, so this is just the same definition. It's a little bit different because now we have here infinity, so x is large. This is a little bit different, not close to some given number. Okay, but essentially it's similar. And for this situation here, you have a similar definition. Okay. Now in this situation, for a given epsilon, you have to find m such that m normally small, such that this here holds whenever x is smaller than m. Okay, it's just the same definition, similar. Maybe you know already from high school that such a line is called horizontal asymptote of a function. We already saw vertical asymptotes, so now this is here we have horizontal asymptotes, and just keep in mind that it's not necessary that, of course, the function can cross also a horizontal asymptote, like the function could another example, another situation how the function is approaching 1 can be as follows. For instance, like this here. Okay, so it's, of course, if you have a horizontal asymptote, the function can also cross the asymptote, okay? It's not, a horizontal asymptote is not a line where the function is getting closer and closer but never reaching it, okay? Because in this situation, you see it can cross the horizontal asymptote. Because some students tend to think that the asymptote is a line where the function is getting closer and closer but never reach it. It's not true for a horizontal asymptote. So maybe just to recall this definition. Okay, so some function y is equal to some line, horizontal line, is called horizontal asymptote. If so, this is terminology. If either the limit of f of x as x tends to infinity is equal to L, or the limit of f of x as x tends to minus infinity is equal to L. Okay, and they normally tell you quite a lot about the shape of a function. They are actually quite important. Horizontal asymptote. What is the reason for this? The reason is as follows. If you use your, for instance, Maple to plot a function, the function will always be plotted. You never will understand what the function is doing as x tends to infinity or x tends to minus infinity, because you have your range for x, and you can just plot the function over this range. So figuring out horizontal asymptotes of a function is something a graphing device will never be able to do. I mean, if you just plot the graph, okay? So this tells you quite a lot about the way a function behaves. Okay, now, for this notation, limits, this should be at infinity. For limits at infinity, we have also limit laws. Okay, so because the next step is again, okay, how to figure out if given a function you want to figure out the limit at infinity, how to do it. Now we use a similar approach as for the other limits. Namely, we first figure out the limit for some easy functions. Then we prove limit laws by using the epsilon delta definition, and then we can build more complicated functions from the basic functions and the limit laws. Now, the first important case is that the limit as x tends to infinity of 1 over x is equal to 0, and the limit of 1 over x as x tends to minus infinity is also equal to 0. So 0 is an asymptote of this function here. Now, for instance, for this here, just once to use the epsilon delta definition. So what you have to do here is you have to make the distance between 1 over x and 0 smaller or equal than epsilon whenever x is large. Now from this you already see, okay, that the choice m is equal to 1 over epsilon will do it. Okay, so in this case it's very easy. So for this choice here, you see if x is larger than 1 over epsilon, you get that 1 over x is smaller or equal than epsilon. You can also put the absolute value, because if x is larger than 1 over epsilon, it's positive. Okay, so this proves already, using the epsilon delta definition, this proves already this limit relation. This limit relation is proved similarly. And now I'm not going to prove the limit laws. I'm not even stating them. I just tell you that all the limit laws are true also for limits at infinity. Okay, so all limit laws also hold for limits at infinity. Okay, so for instance, you have the following result. Let R be a rational number, then the limit as x tends to infinity, R larger than 0, then the limit as x tends to infinity of 1 over x to the R is equal to 0. And the same happens for the limit x tends to minus infinity, 1 over x to the R is equal to 0. Now, the reason here, in this case, of course, I need some assumptions. So for R, there are some restrictions here. So actually, forget this one. Now, the reason why I just stick here, of course, you know that if you choose any real number, this is true as well. The reason why I stick here to rational numbers is because also, if you look at the limit laws, we have just proved it for rational numbers. And this actually has some reason, because when we introduced functions like this here, this symbol, we were just able to do it for rational numbers. So if you have here irrational number, it would be more complicated, because this symbol, we have never defined it precisely. So using the epsilon delta definition wouldn't make a lot of sense, because we do not really understand what the function is. So we cannot do it that precisely. Now, you know already how to apply this. So this is quite useful. So you know already how to apply this. You have seen many examples in high school. So for instance, if you are asked to find out the limit as x tends to infinity of x to the cube plus 5x over 2x to the cube minus x squared plus 4. Okay, so now, of course, one way would be, once more, one way to prove this, to prove that the limit is equal to 1/2, as you know already, would be by using the epsilon delta definition, but a little bit complicated for such a function, because you have to look at this function minus 1/2, the absolute value, and have to figure out, okay, when is this, how large to make x, that this is smaller or equal than a given epsilon. But we do not have to do this because we know that all the limit laws, and we know also this relation here. And you know already what the basic trick is, namely you multiply a numerator and denominator with the leading power 1 over x to the cube. Okay, so you cannot, of course, you cannot use the limit law directly, okay, because the limit of the numerator does not exist. So you have to do something like this before you use the limit laws. Now you get, okay, this is the limit as x tends to infinity, 1 plus 5 over x squared over 2 minus 1 over x plus 4 over x to the cube. And now you can use the limit laws because the limit now of the numerator exists is equal to 1. Here again you use the sum rule. You use the fact that the limit of a constant function is a constant function. You use this here, okay, and you do the same for the denominator, and you see, okay, that the limit in fact is 1/2. Okay, and the advantage once more of this approach is that you do not have to find the m in the epsilon delta definition here. Okay, you do not have to find to figure out, okay, if you look at this function minus this one, how large do you have to make x such that the distance is smaller or equal than epsilon, which would be a much more complicated problem. Okay, so this is one easy example. Another easy example. Do we still have time? Yeah, one more example. Okay, so if you are asked to find horizontal asymptotes of such a function, of course this is not much more complicated. So we are interested in the limit as x tends to infinity. Now we can write this as x minus 9 over the square root of 4x squared plus 3x plus 2. Okay, and again we cannot use the limit laws because if we just put the limit into the numerator would be infinity. Okay, so we have to first to do something in advance. Of course, you all know already what to do. So you take out here 4x squared, so you have 2x here, and then you divide the numerator and denominator both by 1 over x. So you get 1 minus 9 over x over 2, and then you have here 1 plus 3 over 4x plus 1 over 2x squared. And now actually you can really apply the limit laws because the limit of the numerator is equal to 1. The limit of the denominator you have here, you can take out the constant. We have seen that for a square root you can take in the square root, also this, you can take in the limit, also this holds, and here you have 1, so you get 1/2. Okay, so 1/2 is an asymptote of this function. Now, what happens with the limit x tends to minus infinity, x minus 9 over square root of 4x squared plus 3x plus 2. Okay, so here's something which students quite often forget, namely, if you take out 4x squared, okay, if you compute the root of 4x squared, because x is negative, so in this case you get minus 2x. Okay, so you have here 1 minus 9 over x, and then you have here minus 2. Okay, and then the square root of the rest is just the same, 1 plus 3 over 4x plus 1 over 2x squared. And if you take the limit now, you see you get minus 1/2. So 1/2 and minus 1/2 are both horizontal asymptotes. Okay, so here if you compute the root of something like this here, and the number is negative, okay, do not forget the minus here. And one final example, because I told you all the limit laws are true, so also the squeezing theorem will hold for limits at infinity. So if you are asked to find the limit as x tends to infinity of, let's say, the floor of x over x squared, now you see that actually you know that the floor of x, okay, is smaller equal than x. That's the definition. And you see it's larger than x minus 1. Okay, so you see that if x is large, so this is positive here. So if you divide everything by x squared, you get 1 over x minus 1 over x squared is smaller equal than 1 over x. Okay, and now as x tends to infinity, this here will tend to 0. This here will tend to 0 as well. So from the squeezing theorem, you see that this limit exists is equal to 0. Okay. Okay. So for limits at infinity, everything is true. Okay. Also the squeezing theorem, and this is an example which tells you how to apply the squeezing theorem.